Welcome back to another explainer. Today, we're diving into source material covering one of the most heavily tested and honestly most often misunderstood areas of the NEC 2023 exam prep, branch circuit and feeder conductor sizing. If you've ever been banging your head against the wall trying to figure out exactly when to multiply, when to divide, and which code table to actually use when sizing wires, well, you're in the right place. Let's get focused and decode this whole shebang together.
Okay, let's dive into this. Picture this exact job site scenario. You've got a 145 amp continuous load. You've got 8 current carrying wires, all just crammed into a single pipe. Sizing the right wire for this situation is exactly the kind of multi-step code puzzle we're going to unpack today. By the end of this explainer, the logic behind solving this is going to make perfect sense, for sure. To get us there without the cognitive overload, here's our roadmap. 1. The Ampacity battle plan. 2. Terminal temperature rating limits. 3. The continuous load penalty. 4. Heat and conduit fill. 5. The ultimate math showdown. And 6. Job site reality check.
Starting off with Section 1, the Ampacity battle plan. Before we even think about crunching numbers, establishing a clear, repeatable battle plan is the absolute secret to conquering Articles 210, 215, and 310. We need to define our baseline metric so we're all on the exact same page. The NEC defines ampacity as the maximum current, in amps, that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. Sounds simple enough, right? But it's those tricky conditions of use that start penalizing our wires.
And that brings us to our very first villain in this story: time. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. When a wire is carrying a heavy load for over 3 hours, it gets hot. The code recognizes this reality, and as you'll see, it forces us to adjust our math to keep everything safe.
Which takes us right into Section 2, Terminal Temperature Rating Limits.
And this brilliantly illustrates a trap that catches so many apprentices, sizing a wire based solely on its own insulation rather than its weakest link. You could have a THHN wire rated for 90 degrees Celsius, but it's paired with a terminal lug only rated for 75. THHN is fantastic for heat, but if the current heats that wire to 85 degrees, sure, the wire's fine, but the lug? It literally melts. You must play by the lug's rules.
Because of this bottleneck, Section 110.14c steps in. It dictates that even if you have that rugged 90-degree THHN wire right there in your hand, if it connects to a 75-degree terminal, you are legally bound to size that conductor from the 75-degree column in Table 310.16. Basically, you have to cap your wire's potential to protect the terminal.
Moving on to Section 3, the Continuous Load Penalty.
Now that we know which column to look at, let's look at the first specific mathematical penalty conductors face in the field. Remember that 3-hour mark? Per Section 210.19a1, where a branch circuit supplies continuous loads, we have to multiply that continuous load by 1.25. That is a 125% penalty just for leaving the equipment on for 3 hours.
This calculation forces us to artificially inflate the load on paper. If you've got 100 amps of non-continuous load and 100 amps of continuous load, you don't size for 200 amps. No way. You size for 100 plus 125, which gives you 225 amps. We inflate the number so that when we actually check the tables, we are forced to pick a physically thicker, safer wire that can handle that sustained heat.
Let's move to Section 4 and see how this builds: heat and conduit fill.
Because time isn't the only thing testing these wires. Cramming too many wires into a single pipe or running them through a blazing hot attic drastically reduces a wire's ability to dissipate heat. When you have an excessively high ambient temperature, or more than 3 current-carrying conductors in a raceway, the code forces us to divide our load by specific adjustment factors found in the 310.15 tables. But, side note here, not all wires count towards that fill. A neutral conductor only counts if it carries the major portion of the load. And equipment grounding conductors, they never count toward this specific penalty.
Now, what's really interesting about this is a very specific high-yield exam number you should memorize: 0.82. If you've got a 90-degree rated wire, like THHN, operating in a 120-degree Fahrenheit ambient environment, Table 310.15b11 tells you the correction factor is 0.82. So if you have a 95 amp load, you literally divide 95 by 0.82. That inflates your requirement to 116 amps, again forcing you into a larger, safer wire.
All right, here we go. Section 5, the ultimate math showdown. Here is a trap the exam loves to lay for you.
What exactly happens when a wire faces both time penalties, like a continuous load, and environmental penalties, like too many wires in the conduit, at the exact same time? Do you stack the penalties against each other? Do you multiply the load by 1.25 and then divide that new massive number by the correction factor? Absolutely not. You do not. The golden rule of the NEC here is, run them separately, pick the larger result. The source material emphasizes that you evaluate the time penalty in total isolation. Then you evaluate the environmental penalty in total isolation. Never stack them.
Here is your precise three-step sequence to tackle complex exam questions where both time and environmental factors are in play. Step 1. Multiply your load by 1.25 to correct for the continuous load. Step 2. Take the original, uninflated load and divide it by your environmental correction factors. Step 3. Look at the two resulting numbers side by side, compare them, and size your wire based entirely on whichever resulting number is larger.
Let's bring this all together in Section 6, Job Site Reality Check.
Let's bring this theory into practice and walk through a realistic job site problem to prove this battle plan works flawlessly every single time. Imagine you're using THW copper conductors to supply a 50-amp continuous load with 75-degree terminals. But there are 7 current-carrying conductors in the conduit. Let's say 3 hots, 3 load-bearing neutrals, and we already know we aren't counting the ground. Let's run the isolated math. Step 1, continuous. 50 amps times 1.25 equals 63 amps. Step 2, conduit fill. We look at table 310.15c1 for 7 wires, which gives us a 0.70 adjustment factor. 50 amps divided by 0.70 equals 71 amps. So, the crucial point is the showdown. We compare the 63 amps against the 71 amps. 71 amps wins. The conduit fill penalty actually outweighed the continuous load penalty here. To safely carry 71 amps, we check our 75-degree column in table 10.310.16. A number 6 wire is only good for 65 amps, that's too small. But a number 4 THW wire is rated for 85 amps. The larger number 4 wire is our winner. Let's return to that hook question from the very beginning of this explainer. A 145-amp continuous load with 8 current-carrying conductors in a conduit, using THWN copper to 75-degree terminals. Step 1. 145 times 1.25 equals 181 amps. Step 2. 8 wires means a 0.70 factor. 145 divided by 0.75 equals 207 amps. 207 is larger than 181. We look at table 310.16 in the 75-degree column for THWN. We need a wire that can handle at least 207 amps. Boom! A 4/0 AWG is rated for 230 amps. There is your answer, effortlessly outputted by our 3-step method.
By isolating your penalties and respecting your terminal temperature limits, you can successfully navigate these Article 310 ampacity calculations like a pro. But this leaves us with one final critical thought to ponder. You now know how to perfectly size your wires. But once you have those thick wires in your hands, do you actually know the rules for sizing the physical conduit they have to be pulled through? That is a puzzle for another time.